Okay, we're back again with the physics video lecture. Physics, that is to say psci 168 video lecture 26. And I have up on the table the demonstration that didn't work last time. So I went and practiced it. I'll tell you how I fixed it after I make this thing work again. We're talking about heat transfer mechanisms, and this was the third of three. So I'll just go ahead and write them down again. Heat transfer mechanisms. We have conduction, which at the molecular level is with direct molecular collisions. That's when you touch something and it feels hot. We have convection, which is fluid flows. Air currents, water currents can carry heat, and actually quite a bit. And the third one is electromagnetic radiation. So what I'm trying to do is ignite the matches on this side just by turning on a really bright light on this side. So I'll go ahead and give that another try, and then we'll continue to discuss it and its ramifications. So there's the bright light, and this is not going to take long this time. We had ignition, and those are the burning matches. Okay. I'm going to blow them out, hope the smoke doesn't bring down a rain from the sprinkler system, but I don't see any sprinklers. Hope it doesn't set off the smoke alarm. Okay, so yeah, we ignited those matches from over here, what we wanted to do last time. So why didn't it work last time? Right? There's got to be an explanation. The explanation is very simple. The focal point of this mirror is right where the matches are now. It's about this far from the back. And what happens is the light rays come in and they all bounce off and end up at the same point. So you get a big concentration. And last time, for some reason, I don't know who to blame, but this, you can even find it in the video, these matches were set out much farther. So yeah, I had to go back and monkey around with it a bit and bring it back to the focal point. And then it worked. So we have just demonstrated heat transfer by radiation. I have to say a fair amount now about electromagnetic radiation. That's also a topic for the subject of electricity and magnetism, but obviously we have to talk about it now. And remember, the heat transfer, it's always from the hotter, there's the direction of Q, to the colder, the cooler, the less hot object. So that's the direction of heat transfer. And here we, after all, had a very, very hot, bright light bulb, and over here we just had room temperature. But the whole situation generalizes quite a bit more. So I'll go ahead and continue with this radiation discussion. And then I have a really interesting project for us to do for the homework. So the radiation, and I probably wrote this last time, it's electromagnetic radiation. It is not radioactive radiation. Okay, those are different things. That just is radiation, as in, you've heard the expression radiant heat. You have heat lamps and things like that. So that's what we're talking about, electromagnetic radiation. But that's a really rich subject. We're talking about electromagnetic waves. And I have to go into this a bit. So electromagnetic waves. Now when you think of a wave, you think of a wave on water, for instance. And that's a good place to start, because a wave on water has, here I'll use blue, has what we call a wavelength and a frequency. So I'll start with a water wave. Okay, so you imagine you're at the beach and some waves are coming in, some swells. And in a situation like this, we say that the distance between peak and peak, or trough and trough, is the wavelength. So lambda, it's one of our Greek letters. We had that Greek alphabet that everybody downloaded. So lambda is the wavelength. And we can measure it in meters if we want. And light, which is what this was here, light is an electromagnetic wave, and it also has a wavelength. But there are shorter and longer wavelengths. So we have to look on the one hand at the wavelength, and on the other hand at the frequency. So F is equal to frequency. Now we're talking about waves in general. They can be said to have a wavelength and a frequency. Let's send this up here. And the frequency is how often. So if you saw a water wave, frequency is a number, okay? Number per unit time. So if you had a wave coming through here, let's go ahead and draw another wave. So suppose we had a wave and it's traveling, okay, but the distance between these peaks remains the same. So we call that lambda. But suppose you are a swimmer. You're a swimmer and these waves are passing. If you've ever done this before, the wave passes you, you kind of rise and fall as the wave passes under you. So you bob up and down. And you bob up and down with the frequency, okay? Whereas the wave has the wavelength. So frequency equals number per unit time. The number of cycles, I'll just write number of cycles per unit time. So what happens if you multiply these two together, lambda times F, you've got a wavelength times the number divided by time, so you have a length over a time is equal to the wave speed. Okay. And C, in the case of electromagnetic waves, is actually the speed of light. And the speed of light is enormously fast. It's 3 times 10 to the 8 meters per second. Okay, so I have to introduce these concepts, not because we're going to actually see these wavelengths of light, nor are we going to bob up and down on them like we do in the ocean, but rather because there is a very broad, what's called spectrum of either wavelengths or frequencies. You'll notice they're just inverse to each other. So you multiply them together, you get a constant. So the wavelength and the frequency are inverse to each other. Now, let's go ahead and make a graph in terms of, we could even make 2 graphs. Let's just call this the spectrum of electromagnetic waves. That's an M, E-M, electromagnetic waves. And if we do frequencies, it'll be the inverse of the wavelength. But the point I want to make, we'll do wavelengths. So lambda is in meters. The point I want to make is that what's called visible light is a very tiny part of all of the wavelengths of light. In fact, for my graph, I'm going to make this even smaller. I'm going to call this the visible. Okay, this is visible light. And it's measured like this. We have 400 times 10 to the minus 9 meters. And what is that? That's 4 times 10 to the minus 7 meters. That is blue light. Blue. So the different colors depend on the different wavelength. And here I'll even use red. We'll say 900. Or not even 900, we'll say 700. 700 times 10 to the minus 9 equals 7 times 10 to the minus 7. You'll notice these are very, very short lengths. A millimeter is 10 to the minus 3. So these are so short you cannot see that. You cannot see lengths that small. Meters, should have said meters here. And that's red light. Okay. So between red and blue is all you can see. So as the wavelength gets longer, so I'm just going to shade this in here. There's the visible part of the spectrum. As the wavelength gets longer, you can no longer see it. But just on this side of the visible red is what's called infrared. And you can feel infrared. So if you feel warmth on your skin, infrared, okay? If you feel warmth on your skin from a light, that's infrared. And over here, also beyond the visible, is what's called ultraviolet. And you can't feel it until it gives you a sunburn, okay? So infrared you'll feel as heat, ultraviolet will do damage to your body, and you'll feel it as sunburn eventually. And then even between infrared and ultraviolet is a very small spectrum, and the lengths go all the way up to meters and even more, radio waves and stuff, and they get much, much smaller as well. So the electromagnetic spectrum is enormous, amazing, and you know, for a homework, see if you can find some good graphs, download some nice pictures, some nice images, explanations of the electromagnetic spectrum. Okay. So you want to add those into your download that. You'll get something a lot better than we can draw right here. And you can either get the wavelength version or the frequency, and in fact, since they're inverse, you'll find one with the wavelength on one side and the frequency on the other. Okay, the longer wavelength is the lower frequency, and vice versa. Okay, so that is something we have to talk about. This electromagnetic radiation here, we saw visible light. This light bulb has all frequencies, a very broad range being emitted. What we see is just that visible part, okay? And all the colors that are being emitted mix to produce white, which is what, we see that. But it's actually emitting all the different wavelengths. So yeah, that's a whole interesting subject in its own right. And we need to know it because energy is transmitted that way. Thermal energy, right? It's a heat transfer mechanism. Thermal energy goes from one place to another. It doesn't need a medium, so it's not conduction or convection. It can go across millions of kilometers, hundreds of millions of kilometers of space. Empty space, just a vacuum. It shows up and then it provides heat. Okay. Also, in terms of this, I'm going to add a little more technical discussion. So in terms of this energy going from hot to cold, there is the Stefan Boltzmann Law, or just Stefan's Law, we'll call it. We have power radiated. So power is radiated by an object of temperature T as measured in Kelvin. Now the fact is, this very hot light bulb that I had here was just hot. That's really what's giving off the heat. It's so hot that it's radiating a lot of energy, light, heat, and everything. And there's a law for that. And I'll go ahead and put that down. We're not going to calculate with it, but I want you to see it. Because the same amount of power that is radiated could also be absorbed by an object. So the power that's radiated, I'll put that as a note underneath here once I write it down. Sigma EA, we're not going to worry about these constants. This is the area of the object that's radiating. These are some natural constants. It goes as temperature to the 4th power in Kelvin. And you know those Kelvin numbers are pretty big. So temperature to the 4th power, that's the power radiated by an object. But it's also the power that's absorbed. So I'll write here radiated or absorbed. So yeah, which one wins out? You could say the higher temperature wins out. So if I have a higher temperature here and a lower temperature object there, and they're radiating towards each other, this one's absorbing due to the higher temperature, and it's absorbing the higher temperature, and what's more with feeling? So it's radiating at a higher temperature, and the side that's absorbing is at a lower temperature. So it's a net of two expressions of this type. It'll be the T higher to the 4th minus T lower to the 4th would be the net radiation. Okay. So that's again just to remind us that the energy is flowing, the net energy flows from the higher to the lower temperature. Another way to put it is, when this thing is on, it's radiating a lot of energy, but this is also radiating energy as we speak. Okay, they're both radiating, but this one is radiating much, much more, and the net effect on this one is it's absorbing. And remember, because Kelvin goes down to absolute 0, even an ice cube is radiating some energy. And that gets us to the concept of night vision, among other things. Okay. Since that's electromagnetic radiation, it can be focused, it can be reflected, it does everything that visible light does. And so it's possible to get a sensor that will be sensitive to infrared, and then you can get a heat map. As opposed to a map of visible light, you can map things out according to the heat that they give off. And that's what I want to talk about next. So we've got these heat. In fact, we're going to come back to these 3 heat transfer mechanisms, but I've said enough about the radiation. So I want to go into the heat map. And this is what I'm going to turn into a very interesting assignment. Let's check the time we've got going on here. Perfect. Okay. Okay. So I had mentioned the fire in the Sierra Nevada And this current fire season, we have some really major fires in our local mountains. So I want to send you guys out into the internet to look some of these things up that I'm going to discuss right now. Okay. So this next topic is heat maps, temperature maps. Yeah. Okay, so we have local forest fires. I had shown you that book about fires in the Sierra Nevada and talked about the fuel load and how the burning fuel produced a lot of heat, and that was the topic. Well, now we actually can go into this a bit further. What we have is the creek fire currently up in the local mountains. And here's what I want you guys to do, and I think you'll find this really interesting. So the first thing is you're going to do a search for, you type into your search creek fire heat map. Creek fire heat map. We're going to want to get a lot of screen captures printed out on this project. Okay, so you search for the creek fire heat map on your search engine, and what comes up very near the top is interactive map of creek fire near Fresno. So I'll put this in quotes. Interactive map of creek fire near Fresno. This is some online journal, pressdemocrat.com. But I just get the page from here. Because it's somewhere on their very large website. Interactive map of the creek fire near Fresno. Okay, so you open that up, and you got to click through a few various and assorted things. You open it up and you eventually get this map, and you'll have in the middle of your page some, roughly square area, and you'll know it's right because down here is Fresno, about that big, and then in the map kind of centered is this creek fire. Actually the shape is changing now, but okay. You've got the, I don't have to show the shape. Okay, you've got the creek fire, and you get quite a bit of red dots around here. So there's your creek fire map, and it's shaded in somehow. Okay. So you get this map, and it's an interactive map. You can zoom in and out on that thing, and that's where it gets interesting. So we wanted to, by the way, I'm looking at this still, we wanted a screen capture or a printout of some good electromagnetic spectrum. Here we want a printout of this, so I'll just write screen capture. We want one of these, and then we're going to zoom in and inspect it. So 2, open, and screen capture, and I'll keep going here. So what happens when you zoom in is very interesting. Okay, so I'm keeping some numbers going here, so next will be 3. Okay, so 3rd, zoom in, and you're going to zoom in on the red area there, and depending upon your computer, you know, you click different buttons or turn different wheels to zoom in, but you can zoom in very nicely. And up around this part of the map, where it is pretty red, Lake Edison, local reservoir. By the way, part of a large hydropower system. So zoom in to, I'll just say, the Lake Edison region. And when you zoom in enough, you start to see the following. You know, there will be some area like this with many red dots. Okay. So these red dots, larger, smaller, and some yellow dots as well, they are actually infrared data, or data taken from satellites. Okay. So this interactive map of the creek fires is made with using satellite data and automatically updated. So I've been following it for several days now, and there are major changes underway. What you'll find is when you have a lot of these major red dots outside the boundary, outside the fire boundary, let's say here's the fire boundary. If they're outside, that means the fire is progressing there. But we can do more. We can actually click on individual dots, and there's some data about the amount of power that's being radiated, expressed in megawatts, okay, in millions of watts, power being radiated from these dots here. So you're going to zoom in to the Lake Edison area, and you know, I'm just kind of making this up, but Lake Edison is, say, here. Okay, and there's the dam on Lake Edison, so you're zooming in quite a bit. And then you can actually investigate some of these individual dots. You click on a dot, and a little screen comes up with information. Okay. So you want to get a screen capture of this as well. And you know, you can explore different areas of the fire where it's already out and where it's still burning this way. This shows you the active zones of the fire, updated several times a day, because you know, these satellites orbit, they cross the area several times a day. Okay, what else do we have here? Yeah, so red dots outside the boundary mean that the fire is spreading. Okay. Yellow dots are 2 or 3 days old, and the big red dots are within the last 24 hours. So you get a screen capture here for, if you click on a red dot, you can obtain, first of all, how recent the fire was detected. So how recent, it'll say, you know, recent, within 8 hours or 9 hours or 15 hours or something, it'll tell you that. And it'll give an estimate of the amount of power being radiated. Radiated in megawatts, so MW equals megawatts, and mega means a million, so you'll find that. And yeah, once you find this in Lake Edison region, you'll see how you can maneuver around and find anything else you want. So that's 3, that's 4, and if you can get a screen cap from this as well, screen capture, that would be interesting as well. From some point, you'll see some of them are more powerful than others, which indicates a hotter blaze in one place than another. Okay, it gets better though. Let's see how much time we've got here. Fantastic, we've got nothing but time. Okay, so the next step on this project, and I was surprised, I went ahead and scrolled that map all the way down into the Los Angeles area, and I was surprised to see that there were these kind of red dots indicative of a forest fire in the middle of the city. So in the LA Basin, San Fernando Valley, out to San Bernardino, you'll find these seemingly random red dots, and I thought, okay, these must be power plants. But one or two of them were oil refineries, but most of them were, of all things, landfills. Okay, so let's make this part of your project too. So you leave the mountains on that map and you investigate some other region. I had more difficulty doing this for the Central Valley because it's bigger, harder to locate stuff. So let's call this Los Angeles area or just Southern California. So you're looking over Southern California. Let me give some examples. San Fernando Valley. All the way over to San Bernardino. So you're looking over the LA Basin area. And you locate one of these, okay, one of these here. And you don't know what it is because this map here, this heat map, interactive map, doesn't have satellite view on it, okay? It's just more just topographic. So what I did was I found one of these and I didn't actually know what was going on. I went to Google Maps satellite view and zoomed in and compared the two locations, made sure I was on the same spot, and then more often than not it was a landfill. So why don't you guys also look up something down there, and by the way, you can click on it and then find the power output. So why would a landfill show up on a heat map? Okay, if you find and the reason is there's decomposing matter and it actually will build up enough heat. Also builds up gases, they have to vent them. There's a whole industry of landfills. But I did click on a couple of these for landfills and they were about 1 megawatt or less for the whole landfill, but for some reason they show up really well. Some of these forest fire dots were 10, 20 megawatts, for a single dot. So, Southern California, oh, what did I find? I'll just go ahead and write down what I found. I found oil refineries. I found some other kind of industry escapes me now. Did I write it down? Oh yeah, metal fabrication plant. And their red dots are not constant. I went back a couple days later and it had vanished. That means their big heat events are not continuous and daily. Sometimes they are on, sometimes they're not on. But the landfills are pretty much always there. They're giving off a certain amount of heat. And you're surprised at how many landfills there are. Something we usually don't think about, let alone that they give off heat. But this will make a really nice project. So if you print these kind of screen captures, maybe size them so they're not all full page, right? You can arrange them, and the theme of the whole thing is heat transfer by radiation, first of all, electromagnetic radiation, and it's being captured by a satellite. So you can imagine the satellite has a dish on it up there several hundred kilometers up in outer space, and it's aimed at places on the land, and electromagnetic radiation comes in of the appropriate wavelength, and instead of matches, there's a sensor there that senses the particular wavelength and also gives information about its intensity, and from that, the heat map is constructed with information about the location as well as the intensity of all of those red dots. Okay, yeah, this is stuff I just learned myself in the last couple of weeks, and it's pretty interesting. Fits in really well with our topic. So if you can arrange some of your screen captures and leave room to write descriptions on them, what's going on, I think you'll have a really nice little sub project in your book that you're constructing, your notebook. I believe that's, let's see if I have anything else here for us. Actually, I do have one more thing for us. Yeah, I have one more little topic. And because we're talking about megawatts, I want to end with a quick calculation of how much material has to be combusting, has to be burning in order to release a megawatt. Okay. So this last little topic is megawatt of combustion. Good, yeah, I think, yeah. Several screen captures, you're gonna love it. This is gonna be really interesting for you. And you know, whenever you go, when you look at maps, you always learn something. Some geography, you never even know what you're gonna learn when you start studying maps. Okay, so this next topic is heat of combustion. So we've talked about heat of combustion before. How much fuel has to burn to produce a megawatt? Remember, megawatt is a joule per second. So how much fuel burns to release 1 megawatt? And here you'll see our estimates are really nice. We have fuel has about 10, I'm not going to start with fuel, I'm going to start with fat. So we knew that fat has about 9 calories per gram. And we're just going to make a rough estimate, and we know that the mechanical equivalent of heat is 1 kilocalorie, that's a capital C, kilogram. That's 4,186 joules. Okay, I don't have to, not per anything, just joules, no underline. 4,186 joules, okay? And we want to get a megawatt, and of course 1 watt equals 1 joule per second. So let's just do an estimate here. We'll call this for fuel, we'll say 10 calories per gram. Okay. And then we'll round this up to 5,000. Okay. 5,000 joules per calorie. And so calories cancel, we have joules per gram, and we just need to know how many grams will turn this into a million. So if we take 5,020 grams, okay, so 5,000 times 20 is 10 times 10 to the 1, 2, 3, 4, 5, 6. So there's our million, okay? And that'll be joules, so we'll have 10 to the 1 times 5 times 10 to the 3rd times 2 times 10 squared. So here you get it. You got 5 times 2 is 10, so that's 1, 2, 3, 4, 5, 6. Oop. Do I have 7 there? 5 times 2 is 10 to the 1, 2, 3, 4, 5. Oh, 6. There we go. Okay. So, and those are joules. Everything else canceled. So that's a million joules. Okay. A million joules. That means we need 1,000,000 joules per second. So finally, this is for the most concentrated fuel. So 20 grams of fuel per second can release a megawatt. Can release 10 to the 6 joules per second equals 10 to the 6 watts. Okay, now if you're burning trees, you're going to need at least 2 or 3 times this, because the wood is not as concentrated as gasoline, okay, by any means. But remember, that's per second, and that's, you know, that's about an ounce. Okay. So every 15 seconds, roughly, it's a pound. Every minute, it's several pounds. Every hour, you're getting into 250, and over the course of the day, you're burning thousands of pounds of fuel to get a megawatt, and you got a whole forest fire, of course, it's hundreds and hundreds of megawatts all told. Okay, so that's a good calculation here, heat of combustion, and these kind of things can be scaled up to any amount. So we'll do this later, because when we get to heat engines, we're going to come back to the use of fuel. I just had to bring it up now because, you know, it's topical with our little heat map topic. But we can scale these things any amount we need. So we will learn how much fuel it takes to produce 1,000 megawatts, say, for a modern power plant. All that stuff coming up. But this is a really nice detour. So yeah, heat maps, a lot of screen captures, and you'll have a nice section on your notebook. Okay, good. See you guys next time.